Hello students, welcome to this module on the Rayleigh-Taylor or capillary instability, which is part of the course CHE 614 at IIT Kanpur. Today in this module we are going to discuss the instability that happens when you have a cylindrical jet of liquid that comes out of a faucet or a tap. This is a very day-to-day observation that you might have experienced yourself in when you open a tap very gently, you will find that there is a very thin thread or a filament of liquid that comes out of the tap, and this thin cylindrical thread of liquid will not remain cylindrical, and you will see that it breaks into drops. This breakup of a thin cylindrical jet into droplets occurs by this phenomenon of the Rayleigh-Taylor instability, and here the idea, the chief destabilizing agent, the destabilizing mechanism is the surface tension. So the key idea is the following. In general, surfaces or liquid interfaces tend to minimize their surface energy, and the surface or interfacial energy is directly proportional to the surface area of the interface. So if you have a cylindrical thread of liquid or a jet of liquid, right, let's say water, and suppose you argue that it's going to break up into many small droplets. Let's say there are n droplets. Obviously, if the size, let's assume that the size of this original cylinder is capital, the radius of this original cylinder is r, and the radius of these daughter droplets is smaller, and there are n such droplets. These are spherical. Let's assume them to be spherical. If n is way too large, and of course because this cylinder is breaking to give rise to these droplets, volume or mass needs to be conserved. That is, the volume of the original cylindrical jet should be the same as the volume of the n spherical droplets. Let's assume them to be identical in size of radius r. Just for the sake of simplicity in our initial understanding. Now, the volume of the sphere, the conservation of volume, which I have indicated here, implies that pi capital R squared L, which is the volume of the cylinder, must be identical to n times 4 by 3 pi small r cube. Now, this is just mass conservation of an incompressible liquid, which essentially means volume conservation. Now let's also understand what happens to the surface area. What is the surface area of the n resulting droplets? Let's call them Sn. And what is the surface area of the original cylinder? Let's call them S0. We want to know what happens to Sn by S0. Now, if Sn is greater than S0, then there is increase in surface area and therefore surface energy. That is not a feasible process, because you know that systems would like to go to a state of lower energy, and spontaneously speaking, from a thermodynamic point of view, systems always try to go to a state of lower energy. So if Sn is greater than S0, that process is not feasible energetically speaking, whereas if Sn is less than S0, then certainly you might expect that the cylinder has more surface energy than the configuration of droplets. Let's first estimate this. This is simple. This is n times 4 pi small r squared, that is, this is the surface area of a single sphere times n, the number of spheres that you assume that are formed, and this is divided by 4, so 2 pi RL, right? That is the surface area of the cylinder. Okay, now through volume conservation we can figure out a formula for n, like I'm going to discuss. So let's knock off the pi, resulting in n is equal to r squared, capital R squared times L upon 4 by 3 pi r cubed, which I will write it as 3 by 4 small r cubed. So instead of n here, I'm going to substitute this to get Sn by S naught, which is the ratio of the surface area of the n resultant droplets to the surface area of the original cylinder, is nothing but 3 r squared L 4 r cubed. Okay, right? Sorry, I'm going to, this is just n, 3 r squared L by 4 r cubed is just n, and I have to multiply this by 4 pi r squared and then divide this by 2 pi r L. Once we do this, you'll find that this 2 pi cancels, this 4 pi to give 2, and this r square cancels this r cubed to give just r, this r cancels this r, L cancels this L. Finally one gets, therefore Sn by S0 is 3 by 4, there is this r upon small r. Okay, so what we have found is that Sn by S0 is greater than 1 if 3 by 4 r by r is greater than 1, or 3 by 4 r is greater than small r. Okay, so if small r is less than 3 by 4 r, then the breakup of cylinder results in increase in area. But most interestingly, the opposite happens if small r is greater than 3 by 4 r. Okay, there must be a slight mistake in my estimate. It must be 3 by 2, because this 2 is going to cancel 4 to give 2. So let's change the denominator to 2, this denominator to 2, 2. Okay, if r is greater than 3 by 2 r, then this is the cylinder can reduce its surface energy by breaking up into, let's not call it small, into drops of radius greater than 3 by 2 r. Now this is a spontaneous process. This breakup is a spontaneous process because you are not going to supply any energy. This is, when it happens, it's a spontaneous process, this breakup of a cylinder. Capillary breakup, it's also called capillary breakup, is a spontaneous process. Okay, now this is a very simplistic kind of argument. Let's make the argument a little bit more precise. Okay, so what I'm going to do next is the following. I'm going to do a slightly more detailed calculation of what's going to happen when you have let's draw the unperturbed, this is the original cylinder. Okay, this is the original cylinder. Okay, of some radius. Now it is going to be perturbed by sinusoidal perturbations. Let's use like this. Okay, it has to be symmetric, but pardon my drawing, but you get the idea. Now when this is the deformed interface. Okay, due to any perturbation the interface gets deformed. Of course I'm exaggerating the extent of deformation for clarity. These are infinitesimal perturbations, as you know. Now what is going to happen is that you're going to, in this process, gain this much amount of volume. This looks like an area, but you have to revolve it around the axis of the cylinder. Let's also draw the axis of the cylinder. Okay, so if you revolve this around the axis of the cylinder, this piece will become a volume. Right now, although it looks like an area, so this is the volume that is gained, whereas this is the volume that is lost, because now this part is just air or some gas. Okay, the liquid has lost this much of volume, whereas it has gained this much of volume. Now you might think that, well, if this is a sinusoid of the same amplitude, this area is the same as this area, right? But so how can so the volume gained should be the same as volume lost, but that's not the case, because you have to integrate, okay, by taking this area and multiplying it by the 2 pi multiplying by r d theta, and because r is more here and r is less here, okay, and that will result in a greater increase in volume compared to the amount of fluid that is lost. Okay, so the point is, the volume of this crest, okay, is more than the volume of the volume gained by the crest is more than the volume lost by the trough. That means that if I have if I have a original cylindrical jet, okay, now if I were to express this like in this schematic, the radius of this location cannot be the same as the original radius. Let's call the original radius as r0. This r cannot be the same as r0, because if you do that, if I perturb around r0, then the volume of the resultant thing will be more than the original sphere. So for volume conservation to be obeyed, you require that the mean position of this straight interface about which things are perturbed should be slightly smaller. Okay, so this is something that we will show mathematically as well. Right now I'm telling you the physical idea. Okay, now let's do the mathematics a little bit more. So let's assume that the radial location, you have this is the axis of the cylinder, this is the radial location r, and r is given by capital R plus epsilon cosine k z. Epsilon is the amplitude of this deviation, and this distance is r, which is not the same as r0, which is the original cylindrical radius. Now we will figure out a way to calculate the position of r in a moment. Okay, this is the amplitude of the perturbation, whereas this is the wave number, and this is the z coordinate of the cylindrical or axial coordinate of the cylindrical coordinate system, right? So the key thing that you have to realize is that r is not the same as r0 in order to obey volume conservation. So this k is 2 pi by lambda, where lambda is the wavelength of the perturbation. Now let's first figure out what is the increase in surface area, which is basically proportional to surface energy, right? I will put in brackets, or energy due to the perturbation. Okay, so what you have to do is to calculate the area, surface area of the deformed surface, okay, of the perturbed surface. Surface area of the deformed jet is denoted by capital A, which is integral 0 to lambda. I'm going to do the calculation over one wavelength because of course it's a periodic structure. So what you have to do is very simple. Okay, so you know that the in order to find the area, suppose I want you to find the area of the straight cylinder. What you would do is you will take just say that this is pi r squared. Okay, I'm sorry, we are not calculating the volume, we are going to calculate the surface area. We will say that I'll take the circumference of the cylinder, which is 2 pi r, and then I'll multiply it by the length of the cylinder times L, which is 2 pi r L, which is the surface area of a cylinder. Now we don't have a cylinder per se, we have a deformed configuration like this. Okay, now let's take each cross section. Okay, let's take a thin slice. Okay, that very thin slice will appear like a cylinder of length dz, and the circumference of that cylinder is locally 2 pi r, right? So if I do this 2 pi r, and then instead of integrating over you have to now integrate over the arc length ds. Okay, this is the length coordinate. Here it's a straight surface, so you can just walk and then multiply. Because now the cylinder is deforming, this s is the length along the arc of the cylinder, of the deformed cylinder. Okay, so and similarly the volume of the perturbed jet or a deformed jet is simply, again what you will do is, if I want to calculate the volume of a cylinder, I will say pi r squared times L, but here I have to consider pi r squared times dz. Okay, and you are integrating over, and r is a function of z because it's varying, so this is nothing but 0 to lambda, right, pi r squared, the local area, times dz. Okay, now from elementary geometry, if I have a sinusoidal perturbation, this is dz, this is dr, then this is ds, this is the along the arc, so ds squared is dr squared plus dz squared. Okay, so this is something that we know. So this is ds squared, is dr squared plus dz squared. Now I can also rewrite this as ds as dr by dz the whole squared plus 1 to the half times dz. I'm dividing the whole thing by dz and multiplying by dz, right, and that's what leads to this, right? Now because this is small, so if I have when x is small, 1 plus x to the power half is approximately 1 plus half x. Okay, similarly for small x. Similarly, because this is small, I can approximate it as 1 plus half dr by dz whole squared times dz. Now ds is written in terms of dz. I have to substitute this here. Okay, ds is all this times dz, which we have just derived. I'll substitute this there, right, to find the surface area as well as the volume. Okay, so first let's calculate the area. The area is nothing but integral 0 to lambda 2 pi r. Instead of r, I'm going to write r, capital R, plus epsilon cos kz, right? Now times, instead of dz, I'm going to write it as 1 plus Now we have dr dz. I'm going to substitute r is out here. Dr dz is nothing but, if r is capital R plus epsilon cos kz, dr dz is nothing but minus epsilon sine kz. Okay, so if I square this, I'll get, because that's what I need to do here, and I'll get half epsilon squared k squared sine squared kz times dz. Now you should know that we are interested in only terms that are up to order epsilon squared. Even though it's a linear stability analysis, area must be computed up to order epsilon squared, and anything order epsilon cube can be neglected. Okay, so the surface area is nothing but, now everything is per unit wavelength of the perturbation, so I'm going to divide the whole thing by the wavelength. So this is nothing but 2 pi r. So let's first write down the full expression, 2 pi r lambda plus half pi capital R squared epsilon squared. Now a by lambda is therefore 2 pi r plus half pi r squared epsilon squared k squared. Now this appears as if both terms are positive, and therefore a by lambda is always, it's difficult to see from here that how the change. Now what we need to do is we have to calculate a by lambda, this is the changed area or deformed area, minus 2 pi r naught lambda by lambda. That is, this is the change in surface area, is nothing but, so I have to do 2 pi. Okay, now this lambda will cancel out, 2 pi times r minus r naught. So I need r minus r naught, right, to do this. We'll get an expression shortly that will come from volume conservation. First we have to find what is volume of the deformed jet, which is nothing but 0 to lambda. It's pi r squared. R is nothing but capital R plus epsilon cos squared dz, right? If you do this, then volume per unit wavelength is pi r squared plus half pi epsilon squared. Now by volume conservation, this should be the same as pi r naught squared times lambda, okay, and pi lambda. So this is per unit wavelength, right? So I have to divide. Okay, so what we will get is therefore, right, if I equate the two, then I'll get pi r squared minus r naught squared is equal to minus half epsilon squared pi, right? I'm just taking this to the other side. Now I'll cancel the pi. Okay, this is r plus r naught, r minus r naught, minus okay, let's not even do that. Let's write r squared as r naught squared minus half epsilon squared, or I can write this as r naught squared to 1 minus half epsilon squared by r naught squared. Now this is r squared, right? Now this is small, so let's just do this. R is r naught. I'll take square root. Okay, now because this is a small quantity, I can approximate it as r naught into 1 minus half, one more half from the square root, epsilon squared by r naught squared, or r is equal to approximately r naught minus 1 by 4 epsilon squared by, okay, now r naught, because I'm multiplying, right? So that will give you r naught in the denominator. It will cancel one of the r naughts in the denominator. So this is or you can write it as r naught to 1 minus 1 by 4. So this tells you that the new radius, average radius about which fluctuations are happening, sinusoidal fluctuations are happening, is less than r naught because of this factor. This is always negative, because epsilon squared and r naught squared are positive quantities. Alright, therefore what I'm going to do, so from here I can find what is r minus r naught is nothing but minus 1 by 4 epsilon squared by r naught. I'm going to substitute this out here. I need r minus r naught, right? So let me just what I'm going to do next is the change in area is nothing but 2 pi r minus r naught. So change in area is nothing but 2 pi times minus 1 by 4 epsilon squared by r naught squared. Okay, there is one small error here, not error, I forgot to include one term. So a by lambda minus 2 pi r naught by lambda is nothing but this plus, or rather minus, sorry, it's plus half pi r squared epsilon squared k squared, right? So I have to, so this is the change in area. I have to use this expression from here, r minus r naught, and then I also have this half pi r squared epsilon squared k squared, which I forgot to write. So change in area is nothing but you have to write 2 pi, so you have to multiply by 2 pi because we need this, and that will give you 2. This is minus half pi epsilon squared by r naught squared, right? This is one term, and the other term is plus half pi r squared epsilon squared k squared, plus half pi r squared epsilon squared k squared. Now I can write r in terms of r naught. So this is nothing but, change in area is nothing but half pi epsilon squared. Now instead of r I can put r naught because these are higher order terms. So if I put r naught squared, okay, and I take it as common, okay, let me write half pi epsilon squared. Let me take it as common, and you will have there is just one minor issue with respect to this is by lambda. This is there is one minor term, that is this should be not r squared, this is pi r. That was the point I was missing. Sorry about this. This should be just pi r. That was what I was figuring out, because dimensionally things aren't consistent. So this should be pi r. Epsilon squared k squared. Now if I take, and this r is approximately r naught, if I pull out r naught, I'll get -1 plus this. Since I have taken r naught squared, I'll have to multiply by r naught in the numerator. This will be simply k squared r naught squared, or change in area is nothing but half pi epsilon squared by r naught squared. Now this is nothing but, okay, instead of k, I'm going to put 2 pi okay, k is 2 pi by lambda, so this is 4 pi squared by lambda squared r naught squared. Okay, this is nothing but half pi epsilon squared by r naught squared. I'm going to pull out a lambda squared also, so I have to multiply by lambda squared plus 2 pi r naught the whole squared. Okay, so what we have shown by this geometric calculation is that the change in the area of the perturbed cylinder compared to the original undeformed cylinder is approximately half pi epsilon squared by r naught squared lambda squared times 2 pi r naught the whole squared minus lambda squared. Okay, that's what we had here. Now you can ask the question, when is the change in area, let's call it delta A, greater than 0? It will be greater than 0 when 2 pi r naught is greater than lambda. Okay, and the change in area is less than 0 if lambda is greater than 2 pi r naught. That is, the wavelength of the perturbation should be greater than the circumference of the cylindrical jet. Then this is potentially unstable because it leads to such a deformation leads to a decrease in area, whereas when you have very small wavelengths compared to the circumference of the cylinder, such a configuration, such a disturbance is stable. Okay, so this is a very simple way of understanding how the change in area causes a reduction in surface energy for wavelengths that are very or large compared to the circumference of the original cylindrical jet, and if the wavelengths are small compared to the circumference, then such deformations are stable. Okay, so this is the simple physical idea. I'm going to stop here. In the next module we will work out the mathematical analysis of the same problem. Thank you.